Okay, I want to start today by asking you to picture the most violent, destructive, and an absolute force in the universe. Picture the monster in the basement of the galaxy.
You're talking about the supermassive black hole.
Right. Sagittarius A, it's the anchor of the Milky Way. It's the thing we all just sort of accept is sitting there 26,000 light years away, spinning in the dark, eating anything that gets too close.
It's the ultimate incumbent champion of astrophysics.
Exactly. It's in every textbook, every sci-fi movie, every simulation, but
Yeah.
I have a stack of papers here, specifically a study from the monthly notices of the Royal Astronomical Society that is looking to, well, dethrone the king.
It's a bold move, and honestly, usually when someone comes along and says Einstein was wrong or black holes aren't real, you can pretty safely ignore them.
Right, it's usually crackpot territory.
But this is different. This is coming from a serious team of astrophysicists led by Valentina Crespi and researchers from CONICET in Argentina. And they aren't just, throwing wild ideas at a wall. They're using the latest state-of-the-art data to make a mathematical argument that's actually quite uncomfortable to ignore.
And that's the mission for this deep dive. We're going to explore the possibility that the heart of the Milky Way is not a singularity. It's not a hole in space-time.
It's something else entirely.
A dense, solid knot of, well, we'll get to what it is. But if they're right, it changes everything about how we understand our galactic home.
It really does. It's a concept that could create a kind of unified theory of the galaxy, which is something astronomers have been chasing for decades.
So we are potentially rewriting the address of our home galaxy today. But before we fire the black hole, we have to understand why we hired it in the first place. Why were we so convinced that Sagittarius A is a black hole?
It all comes down to gravity. I mean, that's the only tool we really have to see the invisible in deep space. We've been tracking stars at the very center of the galaxy, the S-stars, for over 20 years. Specifically, one very famous star called S2.
S2 is the celebrity star here. It whips around the center like a race car, right?
Exactly. It moves at something like 3% of the speed of light at its closest approach.
Wow.
Which is just incredibly fast. Now, basic Keplerian physics, the same high school math that keeps Earth orbiting the sun, tells us something very specific.
Okay.
For a star to move that fast in that tight of a circle, it has to be orbiting something incredibly heavy and incredibly small.
We're talking about 4.3 million suns packed into a space smaller than our own solar system.
Precisely. And since we can't see it, it doesn't shine like a star, it's completely dark. The only thing in the standard model of physics that fits those dimensions is a supermassive black hole.
A point of infinite density.
A singularity. It's the invisible hand holding the galaxy together.
So, the math works. The orbits fit. The black hole theory explains why billions of stars, planets, and even us orbit the way we do. So why are Crespi and her team trying to fix something that isn't broken? Why challenge the champion?
Because while the model works well, it doesn't work perfectly. And in physics, almost perfect is just a polite way of saying wrong. There are cracks in the foundation if you look closely enough.
Let's unpack those cracks. I was reading through the background on this, and one thing that stood out to me was the faintness of our galactic center.
Yes, that is a big one.
Yeah.
For a supermassive black hole, Sagittarius A is suspiciously quiet.
What do you mean by quiet?
Usually these things are messy eaters. Matter falls in, gets superheated in the accretion disk, and just blasts out X-rays and radiation. We see this in other galaxies. They have these active galactic nuclei that shine like beacons across the universe.
But ours doesn't.
But our black hole, it's incredibly dim.
It's on a diet.
Or it's just not efficient at eating. But there's another weird anomaly that the researchers point to, and this one is really the smoking gun for the skeptics. Back in 2014, a gas cloud called G2 passed incredibly close to the black hole.
I remember this. Everyone had their popcorn ready.
The entire astronomical community was watching. We expected the black hole's tidal forces to just rip this cloud apart.
Certification.
Exactly. The gravity at the nose of the cloud should be so much stronger than the gravity at the tail that the whole thing stretches out like a noodle and gets devoured.
Yeah.
And nothing happened.
Nothing.
Well, not nothing. But the cloud survived. It stayed compact. It swung past the black hole and kept going, relatively intact. That shouldn't really happen if you're skimming the event horizon of a singularity.
Sure.
It suggests the gravity, well, might be softer.
So you've got a dim engine, a gas cloud that refused to die, and according to this new paper, some subtle issues with how the galaxy rotates further out.
Right. It's like doing a jigsaw puzzle where you have to force the last few pieces in with a hammer.
Oh.
They stay in place, but the picture looks a little warped.
So these researchers are asking.
They're asking, what if the pieces don't fit because the box cover's wrong? What if it's not a black hole?
Okay, so enter the challenger, the dark matter core. Now, when I hear dark matter, I usually think of that mysterious, diffuse stuff that hangs out around the edges of galaxies, the halo.
Right.
But this study is putting it right in the bullseye.
And this is where we have to get a little technical to really understand the elegance of their idea.
Yeah.
They aren't just talking about generic dark matter. They're proposing a core made of light fermions.
Okay, let's pause and define that. What is a fermion?
A fermion is a category of particle. Matter, the stuff you and I are made of, protons, neutrons, electrons, those are all fermions. The key rule for fermions is that they're antisocial.
Antisocial.
In physics terms, yes. They obey the Pauli exclusion principle, which basically states that no two fermions can occupy the same quantum state at the same place.
They need their personal space.
They really, really do. They can't stack on top of each other, so if you try to squeeze a bunch of them into a small box, they push back.
And they push back hard.
Tremendously.
Yeah.
This pushback is called quantum degeneracy pressure. It's actually what keeps a white dwarf star from collapsing under its own gravity. Now, contrast that with a black hole.
In a black hole, gravity wins.
Completely. The structure collapses. Everything is crushed down to a single point, a singularity, infinite density.
But with these dark matter fermions, that pressure fights gravity to a standstill.
Precisely. The researchers are proposing that the center of the galaxy is a ball of these specific dark matter particles. They're light, but there are so many of them packed so tightly that this quantum pressure balances out the gravity.
So instead of collapsing into a hole,
they pack together into a super dense, stable ball. It's not a point of no return. It's a physical object, a core.
Okay, so help me visualize the difference. If I'm in a spaceship flying toward the center of the Milky Way, if it's a black hole, I eventually hit the event horizon and I'm gone. If it's this dark matter core, what am I looking at? Is it a solid rock, a cloud?
Think of it like an incredibly dense fog bank. It's not a hard surface like the planet where you would crash.
Okay.
It's a cloud of particles. But the deeper you go, the denser it gets. The proposal describes a cloud-shaped core with two distinct regions. You have this super compact inner core, about the size of the black hole's shadow, and then it diffuses out into a thinner outer halo.
So it's fuzzy.
It's fuzzy, but it has mass, massive mass. And here's the kicker. Because it's a ball of particles and not a singularity, it doesn't have an event horizon. You could theoretically fly through it without being torn apart by tidal forces, assuming the radiation didn't get you first.
That is a wild image. So we're swapping a bottomless pit for a giant ball of invisible fog. But this isn't just a cool theory scribbled on a napkin. The reason we're talking about this now in 2026 is because of the data. The source mentions a specific timeline, right? Regarding the Gaia satellite.
Right. Context is key here. This idea relies heavily on Gaia.
The European Space Agency mission.
Yes. Gaia DR3 Data Release 3 came out a few years ago, back in 2022. It gave us the most precise map of stellar motion ever created.
Ever.
It measured the positions and speeds of nearly 2 billion stars. It was a massive, massive leap forward in astrometry.
And when Crespi and her team plugged that high-fidelity data into their model, what did they find?
They found that the dark matter core model actually fits the stellar rotation curves better than the standard black hole model in certain areas. But this leads to what I think is the most fascinating insight in the paper. It's something researcher Carlos Arguelles calls the continuous substance theory.
I circled that phrase in the notes because it sounded almost philosophical, continuous substance.
It's just so efficient. I mean, think about the standard model of the galaxy right now. You have three distinct components that we treat as separate things.
Right.
One, the black hole in the middle, that's normal, collapsed matter. Two, the stars and gas disk. And three, the dark matter halo on the outside, to explain why the rotation speeds are off. You need a different magic trick for the center and the edge.
It's a Frankenstein monster, a bit of this, a bit of that, all stitched together to make the math work.
Exactly. But the Arguelles and Crespi model says, no. The center and the halo are the same thing.
Wait, hold on. So the thing driving the S-stars in the middle and the thing holding the galaxy together at the edge, it's all one structure.
It is all one continuous distribution of these fermions. In the middle, the pressure and gravity pack them so tight they mimic a supermassive black hole. As you move out, the density just drops, creating the halo effect that dictates the rotation of the outer galaxy.
That makes a lot of sense. It's all the scale problem. You don't need two separate mysteries. a singularity for the middle and a halo for the edge. You just need one substance that varies in density.
It's what we call Occam's razor in science. The simplest explanation that covers all the facts is often the best. And if you can explain the core dynamics and the halo rotation with one single particle type, that is an incredibly elegant solution.
It really changes the mental image of the galaxy. Instead of a solar system writ large with the sun in the middle and planets orbiting it, it's more like the galaxy is an iceberg of dark matter, and the stars are just bits of dust trapped in the ice.
That's a very evocative way to put precisely what this math suggests. We are embedded in this object. We aren't just orbiting it. We are traveling through the thinner layers of it.
Okay, I am with you on the elegance. I love the idea of a unified galaxy, but I have to be the skeptic here.
Please.
Because we have a photo.
Ah, yes. The elephant in the room.
The Event Horizon Telescope, the EHT, they released that famous image of the orange donut with the black center. We saw the shadow of the black hole. It was on the front page of every newspaper. If this thing is a cloud of invisible particles, why does it look like a black hole? Shouldn't we see, I don't know, a glowing ball? Or just nothing?
This is the first question everyone asks. If it's dark matter, why did we take a picture of a shadow? The researchers anticipated this, and their defense is actually quite robust. We have to remember what that photo actually is.
Right, it's not a selfie of the black hole itself.
Correct. Black holes, by definition, emit no light. You can't photograph them. What we photographed was the accretion disk, the hot swirling gas around the object, and the shadow cast by the object's gravity bending that light.
Okay, so we took a picture of the glowing gas around the drain.
Exactly. The researchers argue that this dark matter core would also have massive gravity. It's 4 million solar masses after all. It would still pull gas in. That gas would still pile up, get hot and glow. It would still have an accretion disk.
So the stage lighting is the same.
And because the dark matter core is compact and incredibly dense, and because dark matter doesn't emit or reflect light, it would cast a silhouette. They ran the simulations. To the Event Horizon Telescope, a dense ball of these fermions in a black hole look remarkably similar.
So the photo doesn't rule it out.
Does not. The shadow size, recorded by the EHT, is consistent with the critical density of this fermion core. The visual evidence is, let's say, a tie.
That is incredibly convenient for them, but I guess that's how physics works. If two things behave the same way gravitationally, they look the same to our telescopes.
It's the duck test. If it walks like a duck and quacks like a duck.
But in this case, it might be a dark matter decoy duck.
A dark matter decoy duck. I like that. But you're right to be skeptical. And this brings us to the verdict. We have to be careful not to get carried away by the novelty of this.
So are we rewriting the textbooks tomorrow? Is Sagittarius A officially dead?
Not even close.
Yeah.
No. We need to apply some serious scientific humility here. The expert consensus is still firmly with the supermassive black hole theory. It's the incumbent for a reason. It fits the vast majority of the data across the universe, not just our galaxy.
Right.
We see these jets and energy signatures in other galaxies that really look like black holes.
And this fermionic dark matter is just one guess, right? It's a hypothesis.
It's one hypothesis among several, and honestly, it's not even the most popular alternative. But what makes it significant, and why we're doing a deep dive on it, is that it survives the scrutiny of the new Gaia data. It hasn't been disproven yet, which in high-stakes astrophysics is a victory in itself.
So what's the tiebreaker? How do we find out who's right? Do we have to wait another 20 years?
We might not have to wait that long, but we do need better eyes. The answer lies in the stars that are even closer than S2.
Closer than the ones whipping around at 3% light speed.
Much closer. We need to track stars that are basically hugging that inner core. And here's the key. A black hole is a point of singularity. As you get closer to it, gravity scales up in a very specific, predictable way.
Okay.
But a dark matter core is an extended object. It has a size.
Right, the fog bank.
Exactly. If a star penetrates that outer layer of the fog and goes inside the core, gravity will behave differently. It won't pull as hard as you would expect from a singularity because now some of the mass is behind you or around you, not just in front of you.
Oh, that is cool. So if we see a star's orbit get a little lazy or deviate from the Einstein prediction right at the center, that's the smoking gun.
That would be the signal. It's called orbital precession. If the precession matches the extended mass prediction rather than the point mass prediction, then Sagittarius A is in serious trouble.
It is just amazing that we're still figuring out the basics of our own home address. We think we have it mapped, and then someone says, actually, the foundation might be made of ghost particles.
It's humbling. And that's why this matters. It's not just about labeling an object. It represents a radical shift in thinking. It pushes us to question whether we're looking at a hole in the fabric of reality, a breakdown of physics, or a dense knot of this mysterious substance that makes up 85% of the universe.
It flips the script. Instead of the center being empty space crushed to a point, it's the densest part of the hidden universe.
And it connects the dots. If this theory holds, we finally have a map that connects the center to the edge in one continuous stroke.
So let's wrap this up. We started with the monster in the basement, a black hole. We looked at the cracks in the evidence, the dimness, the gas clouds that survive, and we swapped the monster for a cloud.
A cloud of fermions that mimics a monster.
A cloud that mimics a monster. I love that. It's a good reminder that space is usually stranger than we imagine.
Always.
Before we go, I want to leave you with a thought based on that continuous substance idea you mentioned. It's something that really stuck with me. If this theory is true, the center of our galaxy and the invisible halo surrounding us right now are made of the exact same stuff. We usually think of the engine of the galaxy as this distant, scary thing far away, distinct from us. But if it's all one continuous cloud, are we currently floating through the outer thin edges of the very thing that anchors the galaxy? Are we swimming in the tail of the beast?
That's a profound thought to end on. If Crespi and Arguelles are right, we are far more connected to the center than we ever realized. We aren't just observing the structure, we're inside it.
Something to mull over while you look up at the night sky. Thanks for diving in with us. Keep looking up.